All right, hi guys. We've got the next part of our linear regression here. So this is video number 3. So just to kind of recap, one of the things that we have talked about previously is some of our variables. So x is what represents our independent variable. Y is what represents our dependent variable. And now we're adding a new variable called y hat. Okay, so we call this y hat. And y hat, what this represents is your predicted y value. So one of the things that we're going to be doing with this is we're going to be kind of working through a process where um, we have a scatter plot and we want to get a model. We want to get an equation that is going to be the best representation of that data set. So let's say that we have this data set, kind of a moderate strong relationship. So what we are ultimately going to be doing is we're going to be getting the equation for the line that represents this data set. Okay, so now, this line, what this line represents is the predicted y values. So, based on some given x values, so when I go over to some given x value, I would go up and I would be able to determine what is the predicted y value. Um, so, because this is a straight line, this is modeled with a linear equation. Now, if you remember some of your basic algebra, the easiest formula that we have for a straight line is y equals mx plus b. So we're going to have something similar to that, but just different variables, and we're going to change things around a little bit. So what we use for linear regression is y equals a plus bx. And I'm sorry, it's y hat equals a plus bx. So this y hat, this is your predicted y value. Okay. Now you notice from y equals mx plus b. So make sure you're not getting confused on that. Mx, whatever is with the x, that is always going to be your slope. So it's a little bit confusing because now we're using b as the slope where y equals mx plus b. You guys were so used to seeing b as the y-intercept. So in this case, a is going to be your y-intercept. So one of the things that we will want to do with this is we want to be able to interpret these values. So y hat is your predicted value, a is your y-intercept, b is your slope, and x is the independent variable. So you're going to be able to plug some independent variable value into this equation. And then based on that value, you will be able to get a predicted y value. So again, interpreting this is going to be really important. So a, which again is your y-intercept, the way that we would interpret this is when the independent variable is 0, the dependent variable is a. So when we have the dependent variable is 0, what is the value of the independent variable? Then we have our b value, which is going to be our slope. And the way that we interpret this is for every 1 unit increase in x, y will increase or decrease, and it depends on if your slope's positive or negative, by V units. And we'll see those interpretations more when we do a full example, but that just kind of gives you a little bit of an idea. So let's say, I don't know, let's say this is height and shoe size, okay? So it makes sense the taller you are, the larger your shoe size is going to be. So this makes sense that it would be a positive and moderate to strong relationship. So when we interpret it, we would say for every 1 inch increase in height, shoe size will increase by blank units. So it would be whatever the shoe size is that it gets increased. Maybe it increases by half a size. Now, sometimes the y-intercept can be kind of meaningless. So, for example, can we have a height of 0? If somebody has a height of 0, they're not a person, they don't exist, therefore they don't have a shoe size. So sometimes your y-intercept is not useful, but that's again something that we'll see more when we talk about full examples. Now, the other thing that I want to go over in this video is something called the coefficient of determination. And the coefficient of determination is given by r squared. So what this gives the proportion of variation in y that is explained by the relationship between x and y. Because even if you have a really good model with a really strong correlation, every bit of variation in your dependent variable is not because of the relationship between those two variables. Even if we're talking about height and shoe size, while it makes sense in our heads to say as your height increases, your shoe size increases, that's not always the case. You might have someone who is pretty short but has big feet. So genetics, other factors play into that. So while there is a correlation, 100% of the variation in your dependent variable is not always explained by the relationship between those two. There are always other factors in play. Now, the higher your r squared value is, the better, because that means you have a better model. There exists a stronger correlation between the two variables. So the larger that proportion of variation, the stronger your model, because the relationship between those two variables accounts for more of that variation. Okay. Okay, so now that we have learned, about our equation, we've learned about our variables, x, y hat, r squared. Now what I want to do is I want to show you how to run this in the calculator to get all of these values. So we're slowly kind of piecing together this test. I'm showing you bit by bit, and we're putting together a full test. So then we'll get to the point where we run a full example, and I'll show you what the actual full process and full test looks like. So if you remember in video number 2, we used this same data set. This was temperature and water park visitors. Now, we made the prediction that it was a moderate to strong positive correlation with an R value of about 0.8. So if you don't have this data in your calculator still, go ahead and pause the video and get this typed in. But otherwise, we've got it in here. We're ready to go. So we're going to hit stat, and we're going to go over to tests. Now, all the way down, almost to the very, very bottom, there is something called a linear regression t-test. Okay, so linear regression t-test, almost entirely to the bottom. So we're going to go ahead and choose that. And what you want to do is you want to make sure your X and your Y are properly labeled. So we said temperature was independent and the number of visitors was dependent. And we put our temperatures in L1 and our number of visitors in L2. So that should all be fine. Now, this frequency, you don't ever have to change this. And then this part with these characters, this is beta and I think phi. We don't need to do anything with that either. We're not going to be worried so much about the hypotheses in this test, so we don't need to worry about that. So what you're going to do is go down to regression equation. Now, we want to get this y1 in here because we want the calculator to store the regression equation in y1. So I'm going to show you how to get that y1. If you hit vars, right arrow over to y vars, hit enter for function, enter for y1. Okay, and I'll write all that down. Then we'll go to calculate, and here we have our test. So what we have, some of the information that it's given us is we have TEP, and this is like a test statistic. This is a p-value. We have degrees of freedom, which we're familiar with. We have an A value, a B value, S, which is a standard deviation, R squared, and R. So the ones that we are really worried about for the purpose of this test is going to be A, B, and then R and R squared. So I'm going to take just a second here and write these down. Then I'm going to scroll and I'm going to get... Okay, so here's my information that I have. Now, A and B, what these represent are your slope and y-intercept. And remember, it's backwards of what you think. B is the slope. So we have this equation that is y hat equals negative 2,373.6 plus 31.1x. So this is A, this is B. Now, one of the cool things is because we told the calculator to store that regression equation, if you go to y equals, that equation is already in there and you don't have to do any rounding. Now, if you hit graph, oh, I lost my scatter plot. My plot got turned off. There we go. So I've got my scatter plot. I've got my my model that represents this. So this is the model that is telling me when I know the temperature, I can make a prediction about how many people will be at the water park that day. So the points represent actual values of, what was the temperature, how many people were at the park. But the line represents the predicted number of visitors. Okay, so if I hit trace, here's what I see. So if it's 89 degrees, this model is predicting that there is 392 people at the park that day. And you can kind of scroll along the line. So if the temperature gets up to 92, we're looking at about 486 people. So the line represents the predicted amounts. So this is what we have here. Now, does our y-intercept mean anything in this case? So are we going to see a temperature of 0 where a water park's concerned? And can we have a negative number of people? So my y-intercept in this case has no important meaning for us. Now my slope, I can interpret it. So my slope would be as the temperature increases by 1 degree, the number of visitors increases by 31.1 people. Okay, and you can see from our R and R squared value, R was 0.84, so positive, and this actually puts it in the strong category. And then a coefficient of determination, 70% of the Variation in visitors can be explained by the relationship between these two values.